This will be a walkthrough of the AQA GCSE Physics 2022 Higher Tier Paper 1. Question 1. Figure 1 shows a large wind farm off the coast of the UK. The mean power output of the wind farm is 696 megawatts, which is enough power for 580,000 homes. Calculate the mean power needed for one home. Give your answer in watts. 2 marks. So, what we may be initially thinking is we would need to try and recall our equations for power here. However, we've got a value of homes and we've got a value of power. We don't have any information about time, we don't have any information about energy. So we somehow need to use the values given to us to try and work out the mean power. So the first thing that we would need to do here, as they've told us, is we need to give our answer in watts. Right now we've got a value in megawatts. So we need to convert the 696 megawatts into watts. So a reminder that mega means a million. So we would need to multiply that value 696 by a million to get our value in watts. So here is our value in watts now. We're almost ready to get our final answer. So at this point now, this power is for all of the 580,000 homes. So to find out the power for one home, we would just need to take that value and divide it by 580,000. And if we do that in our calculator, we will come out with the value of 1200 watts. So 1200 watts is our answer. 1.2. On one day, the demand for electricity in the UK was 34,000 megawatts. Suggest 2 reasons why wind power was not able to meet this demand. So thinking about wind power, it's a renewable energy resource, which is great, but it has its disadvantages. Wind is not always going to be around every day in the UK. So that means that the wind is unreliable. It won't always be there. The second thing that we need to think about is, even though the wind might actually be there, will it be enough to cause 34,000 megawatts to be supplied? So wind might not be strong enough to turn the actual turbine. The other thing that could be said is that there just may not be enough wind turbines in the UK. You only find them in rural areas where there's not many people living. 1.3. Some of the energy from the wind used to rotate a wind turbine is wasted. An engineer oils the mechanical parts of a wind turbine. Explain how oiling would affect the efficiency of the wind turbine. 3 marks. So this question is about how to improve efficiency. So we've got to think about this word efficiency. This word efficiency really is to do with how useful an appliance is as transferring that input energy into the useful output energy. So why would an engineer want to oil the mechanical parts of a wind turbine? They wouldn't want to do that to decrease the efficiency. They want to do that to increase the efficiency. So that definitely needs to be our first mark. But how is oiling going to increase the efficiency? Well, with these mechanical parts, they're going to be turning, and they're going to be probably touching each other while they're turning. Every time that happens, there's going to be friction which is going to be applied to these parts, and that friction creates heat, and then that heat, that thermal energy, is not going to be useful. It's going to be wasted. So by increasing the efficiency through oiling the mechanical parts, this will reduce friction. And that definitely means now that either less energy is going to be wasted, or you could say that more energy useful is transferred. One point four. In most homes in the UK, there are many different electrical devices. Explain why people should be encouraged to use energy efficient electrical devices. 2 marks. Okay, so again, our question is linked to efficiency because it says it in the question. So, what is an energy efficient device going to do? So, an energy efficient device will mean that less energy is going to be wasted. And then we've got to think now, why is that beneficial? It's beneficial because if you've got more useful output energy being transferred, that would mean then that really less energy would need to go in to meet that demand. So there'd be less electricity that's needed to be generated. Question 2. Figure 2 shows a rock found by a student on a beach. To help identify the type of rock, the student took measurements to determine its density. So here's our figure with our rock. 2.1. Describe a method the student could use to determine the density of the rock. 6 marks. So a method. So we're thinking about our practical that's linked to density. So from that practical, there are 3 parts to it, depending on the object that you have. You could have a regular shaped object. You could have an irregular shaped object. Or you could have a liquid, with these regular or irregular being solids. So what we need to do is we need to look at our object and then decide which one of these 3 methods would we need to describe here. So looking at the object here, we can see that it's got a little bit of a funny shape. So it's not going to be even. So it's going to be irregular. Regardless of what method we are going to describe, the experiment is about density. So what that means that we will need to do at some point is recall the equation. And to find the density, it's going to be mass divided by volume. So first thing that we would need to do here is we need to somehow obtain the mass and then obtain the volume. So obtaining the mass should be with using a balance. So measure the mass of the object, rock in this case, using a balance. The next thing that we would need to do now is we need to talk about how we're going to measure the volume. So because it's an irregular shaped object, the piece of equipment that we would need is a eureka or displacement can. So the thing that we want to do with this eureka can is fill it up with water. Once we've filled it up with water, we can then place our object into the eureka can. We want to ensure that the object is fully placed in the can. So you can say immerse the rock in water in the eureka can. Now if you remember how this eureka can works, it's a can which has got a little spout that comes out from it. So when the water is just above that spout level, it will then start to come out of the eureka can. So what we want to make sure is we've got something which is next to that spout, which can collect the water, but also at the same time allow us to easily measure the water. So we'd have some scale on it. So just to think about a standard piece of equipment that might be useful, it'd be a measuring cylinder. So the next thing that we want to say is place measuring cylinder next to spouts of Eureka can to collect displaced water. Next is that water that has come out of the can will have a certain volume, and that volume of that water that's displaced will be the exact volume of the rock, the irregular shaped object. So we've obtained the volume now of our rock, and we've obtained the mass of the rock. So what we can just lastly do then is we can use our equation to calculate the density, and that should get us our 6 marks. The student determined the density of the rock to be 2.55 plus or minus 0.1 grams per centimeter cubed. 2.2. What are the maximum and minimum values for the density of the rock? 1 mark. So this value of 2.55 can be varied by plus or minus 0.1. So what we would need to do to find the maximum density is take that 2.55 and add that to 0.1. We do that, we'll get a value of 2.65. So that will be our maximum density of that rock. And then to find the minimum density, we just need to do the opposite, 2.55 minus 0.1, and we come out with 2.45. And those should be our values. 2.3. Table 1 gives a density of 5 different types of rock: basalt, chalk, flint, sandstone, and slate. Densities for all of them. Again, plus or minus values given. These plus or minus values are different though. Which 2 types of rock in table 1 could be the type of rock the student had? So we've got an unknown rock here, but we've got a minimum value and a maximum value for it. We want to see which 2 of these could be our rock that we've studied. So we would need to compare the values that we've just found here to what we find in this table. What we're looking for is any of these values overlapping with each other. So what we would need to do is we need to look at each one of these densities and then either plus or minus it and see if it gives us anything in this range, 2.45 to 2.65. So let's start at the bottom, slate. If we do 2.9 plus 0.20, we'd get 3.1. If we do 2.9 minus 0.2, we get 2.7. Out of the range, so cannot be slate. Sandstone, 2.2 plus 0.2, get 2.4. Minus 0.2, we get 2.0, out of the range. Flint, 2.6 plus 0.1, we get 2.7. 2.6 minus 0.1, we get 2.5. Is that in the range? Yes, it is. So flint is one of our options. Let's find the second one. Chalk, 2.35 plus 0.15. That will give us 2.5. 2.35 minus 0.15 gives us 2.2. That is also in the range. So chalk is good. Basalt, lastly, 2.9 plus 0.1, that's 3.0. 2.9 minus 0.1, that's 2.8. So again, out of the range. So our answers need to be chalk and flint. If we look in our actual options here, chalk and flint is both an option. So that's definitely our answer. 2.4. The student only took one set of measurements to determine the density of the rock. Explain why taking the measurements more than once may improve the accuracy of the density value. So accuracy is to do with how close are your values to the true value. So if all of these points are in the center, that means my accuracy is high. If my points are away from my center, my accuracy is low. The other word that's also kind of linked to accuracy is precision. So if all of my points are here to the side of my target, we can say that the accuracy is low, but the precision will be high. So how are we going to ensure that our accuracy, our values that are supposed to be the true value, is going to be improved? Well, by taking it more than once, it allows a mean to be calculated. So really, this question is about your working scientifically skills. But what does a mean then allow you to do? It allows you to identify those values that don't fit the pattern and remove them. What do we call them? Anomalies. So it allows us to identify anomalies and remove them. Question 3. An engineering company has invented pavement tiles that generate electricity as people walk on them. Figure 3 shows someone walking on the pavement tiles. Use the physics equation sheet to answer questions 3.1 and 3.2. What equation links current, potential difference, and power? So that's going to be our second one if we use our sheet properly, but a reminder that this is an equation that you will need to recall in future exams. 3.2. When a person walks on a tile, a potential difference of 40 volts is induced across the tile. The power output of the tile is 4.4 watts. Calculate the current in the tile, 3 marks. So just to be clear, the word induced means to make, create. So this is our question now where we have to use our equations. So we are just using the equation above. Why? A potential difference is given to us, 40 volts. A power output is given to us of 4.4 watts. So when we're using our equations now, the first thing that we should always try to do is just recall it. So power equals potential difference multiplied by current. As you can see by writing the equation, at some point we will need to rearrange. However, to guarantee ourselves 1 mark, we want to just plug the values in the equation that we've recalled. So first thing, let's check our power output was given to us again. So that's 4.4. That will be equal to our potential difference, which is also given to us, 40. And then we need to multiply that by our current, which is not given to us. So we've picked up a mark now just by plugging our numbers in. So what we can do now is we need to get our current on its own. So we need to move our 40 volts to our other side where our power is. So we need to do the opposite operation to multiplication, which is division. So that means it's going to be 4.4 divided by 40 to find our current. Plugging that into the calculator, that should give us a final value of 0.11 amps. So that should be our answer. Use your physics equation sheet to answer questions 3.3 and 3.4. What equation links efficiency, total power input, and useful power output? Right, so using our equation sheet, our answer should be the top one. 3.4. The tiles are used to power LED lights in the pavement. An LED light has a total power input of 4.0 watts. The efficiency of the LED light is 0.85. Calculate the useful power output of the LED light. 3 marks. So again, we're going to use the same format as we did previously. We're going to recall the equation. Efficiency equals useful power output divided by total power input. We're going to now just plug our values in and guarantee ourselves a mark. So our efficiency given to us is 0.85. Our useful power output we don't know, so we can just put a question mark there. And then we need to divide that by 4.0. So again, we need to get this useful power output on its own. We're dividing by 4.0 right now. We need to move that to the other side. So we'll have to do opposite operation. So that means we need to multiply. So it'd be 0.85 multiplied by 40 this time. And then that will give us a value of 3.4 watts. Question 4. A student investigated the insulating properties of different materials. Figure 4 shows some of the equipment used by the student. So we've got a labeled thermometer, a lid, metal can, hot water inside this can, and then insulation around the can. This is the method used. Wrap insulating material around the can, put a fixed volume of boiling water in the can, place the lid on top of the can, measure the time taken for the temperature of the water to decrease by a fixed amount. Repeat steps 1 to 4 using the same thickness of different insulating materials. 4.1. Identify the independent variable and the dependent variable in this investigation. 2 marks. So, reminding ourselves, what does these terms mean? Independent variable means to change. Dependent variable means to measure. So we need to read our investigation method again and then identify what are we changing. So let's look at some of these words. Fixed volume. That's not going to change. That's our control variable. Measure the time taken. So measuring, we can see then, is going to be our dependent variable. So the time taken for temperature to decrease. Let's keep on reading. Repeat steps 1 to 4 using the same thickness. So again, control variable thickness of different insulating materials. So what does that mean? That we're changing then? It's going to be the type of insulating material. The student used 2 different types of thermometer to measure the temperature changes. Figure 5 shows a reading on each thermometer. So what have we got here? We've got a manual thermometer on thermometer A, and we've got a digital one on thermometer B. So we can already start to think about the disadvantages and advantages of each. What is the resolution of thermometer B? So this word resolution, what does it mean? It means the smallest interval that can be read on a piece of equipment. So if we take thermometer A, how can we find the smallest interval? Well, it would be what the smallest line is. So if we were to read thermometer A, our smallest value or smallest interval would be 1 degree. It's actually asking us for thermometer B. So if this value was to change, what would it change by its smallest amount? Well, there's a decimal point there, so it would actually go up to 87.5 or go down to 87.3. So what are the differences between those values? It's plus or minus 0.1. So that means our resolution is 0.1. 4.3. Thermometer A is more likely to be misread. Give one reason why. Well, as you identified before, one is a digital thermometer, thermometer B, and thermometer A then is a manual thermometer. So for you to understand how to interpret thermometer A, you would need to look at the scale and then how far has the liquid moved. Well, the problem with this is the angle at which you look at it. If you look at it from different angles, you could get different readings. So that will be the reason why. Angle at which it is read may affect measurement. And what this is also known as is called a parallax error. So instead of you describing it as the angle at which it can be read may affect the measurement or the reading, you could just say parallax error and it will mean the same thing. 4.4. For one type of insulating material, the temperature of the water decreased from 85.0 degrees to 65.0 degrees. The energy transferred from the water was 10.5 kilojoules. The specific heat capacity of the water was 4,200 joules per kilogram degrees Celsius. Calculate the mass of the water in the can. Use the physics equation sheet. 3 marks. So by going to a physics equation sheet, we're looking for an equation that is linking temperature, energy, specific heat capacity, and mass. So we find the equation and then we recall it. So energy is equal to mass multiplied by specific heat capacity multiplied by the change in temperature. So again, looking at our values in our question, we plug our numbers in. So energy transferred is 10.5 kilojoules. So we got to make sure we use our standard units. So we need to convert the kilojoules to joules. So to do that, you multiply by 1,000. So that would be 10,500 joules. Our mass we don't know because we need to calculate it. Our specific heat capacity is given to us, 4,200. But we need to multiply that by a temperature change. So looking at our question at the top, they said it decreased from 85.0 to 65.0. So that means our change in temperature is going to be 20 degrees. So picked up a mark already. Let's simplify now. So 4,200 multiplied by 20, that will give us a value of 84,000. So our mass multiplied by 84,000 will be equal to 10,500. So we need to isolate our mass, get that on one side. Opposite operation to multiplication will be division. So it'll be 10,500 divided by 84,000. And that will give us our mass, which will be 0.125 kilograms. (4.5) Table 2 shows the results for two insulating materials, material X and Y, and they've given us the time for temperature to decrease by 20 degrees in seconds. Explain how the results in Table 2 can be used to compare the thermal conductivity of the two materials. So, what does this term thermal conductivity mean? It means how good is something in terms of material at conducting thermal energy, passing thermal energy through it. So, looking at our table in terms of values, we can see that Y has a greater time for the temperature to decrease. So, how can we link that now to this thermal conductivity? So, this means that for Y, it's taking a longer time for it to cool down, because the time for it to take to decrease is greater, longer. So, we can say that straight away. Our thermal conductivity is going to be higher in the material that takes a shorter time for it to decrease in temperature. So the higher the thermal conductivity, the shorter the time it takes for the temperature to decrease. But what does this actually mean? Well, if it's thermal energy that we're talking about, it's really to do with the transfer of energy. So, in this case of our table, X has a higher rate of energy transfer. Question 5. A student rubbed a plastic rod with a cloth. The rod became negatively charged and the cloth became positively charged. Explain why the cloth became positively charged. 3 marks. So, we are thinking now about static electricity. So, our cloth and our rod are here. Once the rubbing against each other has taken place, we are saying that the cloth is now positively charged and the rod is negatively charged. So why is this happening? Well, both of these objects are made from atoms. We know that an atom consists of protons, neutrons, and electrons. We know that the atom in the nucleus is where the protons and the neutrons are found. We know that the electrons are found in the shells orbiting the nucleus. So anytime an object becomes either negatively or positively charged, it's because there's been a transfer of electrons. So we need to state that now based on this scenario. In this case now, if the rod is becoming negatively charged, that means that electrons have been transferred to it from the cloth. And that's what we will say for our first mark. Electrons have been transferred from the cloth to the rod. Now what we need to make sure that we state here is that we demonstrate our knowledge that electrons are negatively charged. So we don't confuse that with some positive charge from somewhere being transferred. So what can we say then about our cloth in this case. The cloth is not gaining any protons. Because remember, the protons have the positive charge. It's just losing the electrons. So the reason why the cloth is positively charged now is because it contains more positive charges than negative charges. Figure 6 shows the negatively charged rod on a balance. So looking at figure 6 now, the rod is on the balance. Insulating material is between the balance and the rod. And then we've got a reading of 102. We've got a reading of 100.25 grams on the balance. Figure 7 shows another charged rod being held stationary above the rod on the balance. The rods do not touch each other. So looking at figure 7 now, there's a little gap between the two rods, but the reading on the balance has changed. It's gone up to 100.35 grams. 5.2. Explain why the reading on the balance increases 3 marks. So let's go back to the figure again. The rods are not touching each other, but somehow the balance reading is going up. So for any balance reading to go up, it must mean that something is pushing down on it, causing it to go down. So this rod is not changing in its mass. So if the rod is not changing in its mass, the only other way for the balance reading to go up is for some sort of force to be applied to this rod that's on the balance. So where is the force being applied from? Well, the only thing that's different now is this rod coming into play, this charged plastic rod. But if this charged plastic rod is causing it to apply a force to our other plastic rod, the only other forces it could be is due to some sort of electrostatic attraction or repulsion, because it's to do with the charge. Now let's think if it was attracting it, then the rod would move towards the charged plastic rod. So that would mean that the reading would sort of go down. So then it means that we can understand then that it's got to be repulsion that is occurring, because the rods want to move away from each other. So if it's repulsion, what does that tell us about this charged plastic rod, which is here? Well, they've told us in figure 6 that the charge that was on the balance was negatively charged. So if it's repulsion, it's to do with like charges, because like charges repel. So that must mean that this plastic rod that is being held is also negatively charged. So let's put all of that information in our answer now. So we can say that the held plastic rod is also negatively charged. This repels the plastic rod on the balance, creating a downward force, pushing on the balance. 5.3. The balance had a zero error. The zero error is not important in this experiment. Give the reason why, 1 mark. So let's go back again to our figure. The question is saying that there is an error on the balance and a zero error. This means, for example, that if we were to take this negatively charged plastic rod off of our balance, there would still be a reading which is not 0. So it could be 0.25, for example. But they are saying that that is not important in this experiment, and we need to think about why. Well, what are we trying to do here? We're trying to investigate whether there is some sort of attraction or repulsion by these rods. We're not necessarily interested in the specific masses of the rods. So what we really are interested in is looking for a difference between our balance with our rod on its own and our charged rod held. So if we say that, that should give us a mark. So we're looking for a difference in the readings. So that does not matter about the zero error. 5.4. A negatively charged rod is held near an earthed conductor. Explain why a spark jumps between the negatively charged rod and the earthed conductor. So let's draw our rod again, and then we can draw some sort of earthed conductor. So the question is saying, why is it that you might see a spark jump between these two objects here? Well, why do you see a spark in any situation? The reason why is because there's a difference in potential energy between two objects, and that's what we call potential difference. So if there wasn't any difference, there would be no spark. So we can first say there is a large potential difference between the two objects. Now what that means now is that the charge will then move. It actually moves in the air, and that's how lightning occurs. But where is the actual electrons or charge moving to? And remember, what is negatively charged here? The thing that's negatively charged is the rod. So it means that it's going to move to the conductor. We need to make that direction clear. Our negatively charged rod has got a difference in potential energy to that of our conductor. The electrons, which is the charge, is then going to move to the conductor through the air. Question 6. Figure 8 shows how electricity is supplied to consumers by the national grid. 6.1. Explain why a transformer is used in the national grid. 4 marks. So this is a typical setup of our national grid now. We've got a power station, which is generating our electricity, and then that moves to a transformer, which goes up to our power lines, and then eventually goes to another transformer, which goes down to our consumer. So you can use that to help you remember what X is going to be and what Y is going to be. X is always going to be a step up transformer. Y is always going to be a step down transformer. So we need to recall those, in this case just X, but then we need to think about why that is important. So we can say now that transformer X is a step up transformer. What does that do? It increases the potential difference. Now, why is this increase in potential difference important? When we think about the national grid, we have to apply our equation for power that we mentioned earlier. So power is potential difference multiplied by current. Now, what we always want is you want some high power. But if we want high power, the two things that we could do is increase the potential difference and increase the current. However, if we increase the current, what that can do now, especially through these cables, it can lead to power being dissipated or lost due to a transfer of thermal energy. Because when there's an increase in current, it always leads to an increase in thermal energy. So we want to avoid that as much as possible. So we still want a high power, so we can increase the potential difference even more. So then that means that our current can be decreased a little bit, so we still have relatively high power. So by increasing the potential difference, it allows the current to be decreased. Then, as I said, that then means that less energy is transferred from the cables as thermal energy. Okay, 6.2. Explain why transformer Y is used in the national grid. 2 marks. So we've already stated now what transformer Y is. We said it's a step-down transformer. Well, why is it a step-down transformer? What is it doing? It's decreasing the potential difference this time. Now, why do you want to decrease the potential difference? The problem is now, when the potential difference is too high, that is dangerous. It can lead to electric shock. So, we want to make sure that when our electricity is supplied to our home, that it's safe to be used. So, decreasing the potential difference makes electricity use safer around the home. (6.3) The town of Hornsdale in Australia has electricity supplied by a huge battery. On one day, the battery transferred 3.2 times 10 to the power 11 joules of energy to the town. The potential difference of the town's electricity supply is 230 volts. Calculate the charge flow to the town on this day. Use the physics equation sheet. Give your answer to 3 significant figures. 4 marks. Okay, so they've given us a hint already in this question that our value's going to be pretty large. The other way that they've given us a hint is by our actual value of energy being in standard form. So we know that we're going to get a value which we need to make sure is at 3 significant figures. So, using the physics equation sheet, what equation can we use which links energy, potential difference, and charge now? So, here is our equation that links them. Energy transferred is equal to charge multiplied by potential difference. So, let's plug in our numbers and get ourselves our mark. Energy transferred, 3.24 times 10 to the power of 11. Our charge we don't know, we need to find it. Our potential difference is 230. We need to move our potential difference to our other side, so we have charge on its own. Opposite operation to multiplication is division. So 3.24 times 10 to the power of 11 divided by 230 will equal our charge. If we do that, we come out with a very, very, very large number. That number is 14086. 6, 9, 5, 6, 5, 6, 2. So we need to get this value to 3 significant figures. So by pressing the right value in our calculator, it gives us a value to 3 significant figures of 1.41 times 10 to the power of 9 coulombs.